Introduction. Life depends upon hydrogen bonding. Life is created from water, and water is a liquid due to hydrogen bonding in its molecules. If there is no hydrogen bonding, then water must be a gas just like air. There would be no oceans, no lakes, and no rivers. The fluids in cells of living bodies also exist due to hydrogen bonding. So, all the living systems depend upon hydrogen bonding. Students, you must be curious to know more about this. Today we will study more in our chapter Chemical Bonding and Molecular Structure. Objectives. At the end of this lesson, you will be able to explain VSEPR theory, describe valence bond theory, define hybridization, know about types of hybridization, explain molecular orbital theory, understand electronic configuration and molecular behavior, analyze bonding in some homonuclear diatomic molecules, define hydrogen bonding, valence shell electron pair repulsion, VSEPR theory. VSEPR theory provides simple explanation for the geometrical shape of different molecules. The central atom of molecules may contain two types of electron pairs. They are bond pair and lone pair. The main points of this theory are: the electron pairs surrounding the central atom repel each other. The geometry and shape of the molecule depend upon the number of electron pairs in the valence shell of the central atom. The repulsive interactions between two lone pairs are different from those between two bond pairs or those between a lone pair and a bond pair. Structure of molecules according to VSEPR theory. Shape of some simple molecules are AB type. This type of molecule is always linear. AB2 type. In this type of molecule, the central atom contains only two bond pair electrons, and these electron pairs will repel each other to attain minimum energy, will remain at 180-degree angle. AB3 type. In planar trigonal structure, the central atom contains only three bond pair electrons, and to minimize the repulsive force, the electron pairs will be arranged at vertices of an equilateral triangle, and the angle is 120 degree. In pyramidal structure, the central atom contains a lone pair and three bond pair electrons due to unequal repulsion. The electron pairs will be arranged at the apexes of a distorted tetrahedron, and the angle is 107 degree. AB4 type. They have regular tetrahedral structure. In this type, the central atom contains four bond pair of electrons, and to minimize repulsive force, the electrons are arranged at the apexes of a regular tetrahedra, and the bond angle is 109.5 degree. AB5 type. In this type, the central atom is surrounded by five bond pair of electrons, and to minimize the repulsive force, the most stable arrangement is trigonal bipyramidal. AB6 type. In this type, the central atom contains six bond pair of electrons, and to minimize the repulsive force, they are arranged at the apexes of a regular octahedron. Valence bond theory. According to this theory, covalent bonds are formed due to mutual overlapping between two atomic orbitals. Greater overlapping ensures the stability of the covalent bond. Extent of overlapping depends upon nature of orbitals and nature of overlapping. Overlapping increases if the orbital remains closer to the nucleus. Since except s orbitals, all other orbitals have directional property. In case of two subshells of equivalent energies, the subshell having more directional property shows greater extent of overlapping. S orbitals show only head-on overlapping. P orbitals show both head-on overlapping as well as lateral overlapping. In head-on overlapping, the overlapping region is more than lateral overlapping. Therefore, stronger bond is formed due to head-on overlapping. Types of covalent bond. The covalent bond may be classified into two types depending upon the types of overlapping: sigma bond and pi bond. Sigma bond. Sigma bonds are formed due to head-on overlapping between two half-filled atomic orbitals along the nuclear axis. Sigma bonds are formed due to different types of overlap. S-S overlap. Hydrogen molecule is formed due to overlap of s orbitals of two hydrogen atoms. The partially filled s orbital of one H atom overlaps with partially filled s orbital of another H atom. This type of overlapping has no directional character. S-P overlap. Sigma bond may form due to overlap between s orbital of one atom and p orbital of another atom. Such type of overlapping takes place during formation of HF molecule. This type of overlapping has directional character. P-P overlap. During formation of F2 molecule, half-filled p orbital of one fluorine atom overlaps with half-filled p orbital of another fluorine atom. This type of overlapping has also directional characteristics. Pi bond. Pi bonds are formed due to lateral overlapping between two atomic orbitals along the perpendicular direction of the internuclear axis. This type of overlapping takes place only in case of two p orbitals, the overlapping zone being small. Hence, pi bond is a weak bond. Difference between sigma bond and pi bond. Sigma bond is formed by the axial overlap of atomic orbital, whereas pi bond is formed by the sidewise overlap of atomic orbitals. Sigma bond can be formed by overlap of SS, SP or PP orbitals, whereas pi bond involves the overlap of p orbitals only. Sigma bond is stronger because overlapping can take place to a larger extent, whereas pi bond is weaker because the overlapping occurs to a smaller extent. In sigma bond, the molecular orbital is symmetrical about the internuclear axis and consists of single charged cloud, whereas in pi bond, the molecular orbital is discontinuous and consists of two charged clouds above and below the plane of atoms. Sigma bond may be present between two atoms either alone or along with pi bond, whereas pi bond is always present between two atoms along with the sigma bond. The shape of molecule is determined by the sigma framework around the central atom, whereas pi bonds do not contribute to the shape. However, they modify the dimensions of the molecule. Hybridization. It is a process of intermixing of atomic orbitals with small difference in energy and belonging to the same atom at the time of bonding so as to give another set of orbitals with equivalent shapes and energies. Different types of hybridization depend upon the type of atomic orbitals which are used for intermixing. Orbitals participating in hybridization must have only small difference in their energies. The number of hybrid orbitals is equal to the number of orbitals participating in hybridization. Hybrid orbitals form sigma bonds and are stronger than pure atomic orbitals. Types of hybridization. The various types of hybridization involving s, p and d orbitals. The different types of hybridization are following. sp hybridization. This type of hybridization involves the mixing of one s and one p orbital, resulting in the formation of two equivalent sp hybrid orbitals. sp2 hybridization. In this hybridization, there is involvement of one s and two p orbitals in order to form three equivalent sp2 hybridized orbitals. sp3 hybridization. In this type of hybridization, there is mixing of one s orbital and three p orbitals of the valence shell to form 4 sp hybrid orbital of equivalent energies and shape. Example. Let's take an example on hybridization. Which hybrid orbitals are used by each carbon atom in the following molecules? Let's see the solution. In this molecule, carbon atoms using sp3 hybridization. In this molecule, carbon atoms using sp2 and sp3 hybridization. In this molecule, carbon atoms using sp2 and sp3 hybridization. In this molecule, carbon atoms using sp2 and sp3 hybridization. Molecular orbital theory. In molecular orbital theory, orbitals are devised for the molecules as a whole. These orbitals consist of nuclei of all the combining atoms lying at a fixed equilibrium distance. Thus, atomic orbitals are monocentric, whereas molecular orbitals are polycentric. Molecular orbitals are formed by combination of atomic orbitals of nearly same energy and proper symmetry. Number of molecular orbitals is equal to the number of combining atomic orbitals. Among the new molecular orbitals formed, half are of lower energy and other half are of higher energy. The molecular orbitals are filled in accordance with the Aufbau principle, obeying the Pauli's exclusion principle and the Hund's rule. Linear combination of atomic orbitals, LCAO. According to Schrödinger's wave equation, an atomic orbital can be represented in terms of its wave function psi, which corresponds to amplitude of the corresponding three-dimensional electron wave. A linear combination of two atomic orbitals can be achieved by addition and subtraction of two atomic orbitals of the individual atoms. If for two atoms A and B, each containing one electron, their wave functions are represented by psi A and psi B respectively. Molecular orbitals of the covalent molecule AB can be represented by psi B is equal to psi A plus lambda psi B.
Psi A
is equal to psi A minus lambda psi B, where psi B is equal to bonding molecular orbital. Psi A is equal to anti-bonding molecular orbital. Lambda represents partial ionic character of AB molecule. Bonding molecular orbit is of lower energy than the atomic orbitals as the electrons feel greater attraction between them. Anti-bonding molecular orbit is of higher energy than the atomic orbitals as the electrons feel less attraction between them. Types of molecular orbitals. Molecular orbitals are designated as sigma, pi, delta instead of s, p, d, etc. in atomic orbitals. Sigma molecular orbitals. Molecular orbitals which are cylindrically symmetric around the bond axis are known as sigma molecular orbitals. Pi molecular orbitals. These orbitals are formed due to lateral overlap between two p orbitals along the perpendicular direction of the bond axis. Electronic configuration and molecular behavior. The distribution of electrons among various molecular orbitals is called the electronic configuration of the molecule. Bond order. Bond order is defined as 1/2 the differences between the number of electrons present in the bonding and the anti-bonding orbitals. A positive value of bond order signifies the stability of a molecule, and a negative or zero bond order indicates that the molecule is unstable or the molecules will not form at all. Higher bond order indicates higher bond dissociation energy and shorter bond length. Bond order indicates the number of covalent bonds in the molecule. Some properties of molecules. Stability of molecules. Let Nb is the number of electrons occupying bonding orbitals and Na is the number occupying the anti-bonding orbitals. If Nb is greater than Na, the molecule is stable. But if Nb is less than Na or Nb is equal to Na, the molecule becomes unstable. Nature of bond. Integral bond order values of 1, 2 or 3 correspond to single, double or triple bonds respectively. Bond length. The bond order between two atoms in a molecule may be taken as an approximate measure of the bond length. The bond length decreases as bond order increases. Magnetic nature. If the electronic configuration of a molecule contains unpaired electrons, then the molecule will be paramagnetic, and if it contains only paired electrons, then the molecule will be diamagnetic. Bonding in some homonuclear diatomic molecules. Hydrogen molecule H2. The value of bond order is 1. The molecule is stable and diamagnetic. Helium molecule He2. The value of bond order is 0. The molecule is unstable and diamagnetic. Oxygen molecule O2. The value of bond order is 2. The molecule is stable and paramagnetic. Number of covalent bonds is equal to 2. Nitrogen molecule N2. The value of bond order is 3. The molecule is stable and diamagnetic. Number of covalent bonds is equal to 3. Hydrogen bonding. It is electrostatic force of attraction existing between covalently bounded hydrogen atom of one molecule and the electronegative atom of the other molecule. This bond comes into existence when hydrogen atom is directly bonded to high electronegative atom. The bond is represented by dotted line. For more effective hydrogen bonding, the hydrogen atom should be linked to the atom with small size and high electronegativity. Hydrogen bond is weaker than ionic, covalent, dative and metallic bonds, but stronger than van der Waals forces. Types of hydrogen bonds. There are two types of hydrogen bonds as following. Intermolecular hydrogen bond. Hydrogen bonding occurring between molecules of same or different substances is termed as intermolecular hydrogen bonding. It causes association of molecules, increase of melting and boiling points, solubility of molecular substance like alcohol, sugar and honey in water. Intramolecular hydrogen bond. Hydrogen bonding occurring within the same molecule is termed as intramolecular hydrogen bonding. O-nitrophenol, salicylic acid are some examples of intramolecular hydrogen bonding. Did you know? Covalent compounds are usually insoluble or less soluble in water. Energy of the separate helium atoms is smaller than that of the system when they are close to each other. They prefer to stay separate and do not form He2 molecule. A water strider or skater bug uses the surface tension of water made by hydrogen bonds to move around. Summary. Let us summarize what we have learned. The geometry and shape of the molecule depend upon the number of electron pairs in the valence shell of the central atom. The repulsive interactions between two lone pairs are different from those between two bond pairs or those between one lone pair and a bond pair. According to valence bond theory, covalent bonds are formed due to mutual overlapping between two atomic orbitals. Sigma bonds are formed due to head-on overlapping between two half-filled atomic orbitals along the nuclear axis. Pi bonds are formed due to lateral overlapping between two atomic orbitals along the perpendicular direction of the internuclear axis. Hybridization is a process of intermixing of atomic orbitals with small difference in energy and belonging to the same atom at the time of bonding, so as to give another set of orbitals with equivalent shapes and energies. Hydrogen bonding is electrostatic force of attraction existing between covalently bounded H atom of one molecule and the electronegative atom of the other molecule.